All right, so let's look a little more deeply at ionic bonding and how it has impacts on the ecosystems and the structures of our planet. So we're going to look at what happens when ionic bonds form and also when they're broken. So when sodium and chlorine are bonded together to form sodium chloride, the one thing to realize is that there's never just one of each atom. In the real world, there are millions and millions of them all floating around. And so for every sodium and chlorine that's attached, there's other sodiums and chlorines, other cations and anions that are drifting around looking for places to bond to as well. And those charges remain, those positive and negative charges. So when you have sodium and chlorine, what will happen is a chlorine will come along and it will see that positively charged sodium and be attracted to it. At the same time, some of those positively charged sodiums are going to find chlorines to be attracted to. So they'll come in and attach on to this ionic bond and form ionic bonds as well. More will begin to line up, and they'll come in from the sides, they'll come in from the top, they'll come in from every direction. And soon you'll start to develop a three-dimensional structure of positive and negative oppositely charged ions attaching together. What begins to form after a little time is what we call a crystal. A crystal is a repeating structure of positive and negative charges that are all lining up to form this sort of repeating pattern. In the case of sodium chloride, it forms a cubic crystal. There are other types of crystals that can form with different arrangements, hexagonal crystals and so forth. But sodium chloride makes a cubic crystal where every sodium, if we take a look at this crystal right here, every sodium is surrounded by 1, 2, 3, 4 chlorines on its sides, plus one on this side and one on the inside, which are hard to see on this. But each sodium is going to have 6 chlorines around it, and vice versa. Each chlorine is going to have 6 sodiums around it. As more and more begin to attach, these microscopic crystals begin to grow into larger crystals that are visible to the naked eye. And the one thing you're going to notice about them is that they always form these cubic patterns. They always form these three-dimensional structures at 90-degree angles from each other. Now, depending on the presence of these sodium and chlorine atoms, you may see multiple cubes that all start to merge together to form larger crystals, but each of those can be broken down into smaller cubes. So you can kind of see it. There's a cube here, and then there's this cube right here, and then there's another cube right here. But the one thing you'll notice is they're always forming these sort of 90-degree structures, 90-degree angles. Remember that the ionic bond is the complete transfer of electrons from one atom to another, because in this case the chlorine's pull is far greater on the electrons than the sodium's. Okay, now we're going to get into what's called solvents and solutions. So because they have positive and negative atoms, these ions, they can actually be pulled apart by substances that also have positive and negative charges. And really it comes down to who's got a stronger pull. So this sodium chloride solid can be pulled apart back into its positive sodium ions and its negative chlorine ions if there's something else present that can pull them apart. One substance that can do that is water. So you know from experience that if you were to pour some salt into water, that the salt crystals will dissolve. They will seem to disappear. And what's happening is that the water molecules themselves are actually pulling these crystals apart. Water molecules are polar. They have positive ends and negative ends. The positive ends are near the hydrogens, the negative ends near the oxygens. And so what happens is that the water molecules will be attracted to the charges of these ions, these chlorines and sodiums, and they'll begin to encircle it, to line up around it. And if you'll notice on here, the water molecules will line up with the negative oxygens attracted to the sodiums, like you see here, and the positive hydrogens attracted to the chlorines. And if enough water molecules team up, they can actually have a pull that is greater than the ionic bond that was holding the crystal together, and they begin to be pulled apart. And that is the process of dissolving or dissolution, where the crystals are being pulled apart and the individual ions are removed and then dispersed throughout the liquid, surrounded by water molecules. There's a video I have that shows an animation of like how this process happens. So take a look at 3.2 on solutions. Because the ions are evenly dispersed and dissolved in the water, it's going to make a solution of salt water. Solutions, by definition, are transparent because the ions are so tiny that they do not block light's ability to move through it. So solutions are always transparent. You can see through them. Now, that doesn't mean that they're not colored. You can have red solutions and orange solutions and blue solutions, but as long as it's transparent, you can see through it, you know that it's a solution. Water itself is kind of a blue solution because water has a tendency to absorb the red light and allow blue light to pass through. You can't notice that at the small scale of a glass, but if you've got a large quantity of water, like in the ocean, then you definitely see that bluish color. Now, if you start removing the waters, perhaps you heat it up and it evaporates away. What will happen is, as the water molecules leave, they're no longer able to hold on to those ions that they were holding on to in solution. And so eventually you get to the point where the ions, the sodiums and the chlorines, start finding each other and reattaching to each other. And at that point, the crystals begin to grow. As more and more waters leave, more and more ions are freed up to essentially attract to each other and start growing those crystals again, and you reform the crystals. And so this process is completely reversible and repeatable over and over. You can dissolve salt into water, you can evaporate the water and reform the crystals, and this will go over and over. The crystals are always left behind, so when water evaporates, only the water leaves as a gas, and all of the ions are present to reform those solid ionic crystals. And so that's what you'll see in a situation like this, where you've got these crystals of salt forming in a dry lake bed, where this was a salt lake that basically the water started evaporating. In fact, we take advantage of that when we want to make something like sea salt. So sea salt is a situation where you have a large, flat, shallow area where you fill it with seawater from the nearby ocean. Typically this is done in hot, sunny locations like the Mediterranean and in tropical environments. The sun evaporates the seawater, salt crystals begin to form, and then you essentially scoop up the salt. Then you allow more salt water to come in from the ocean, evaporate it away, collect the salt, and that's where your sea salt comes from. All right, I've got one more video, ionic bonds, that I'd like you to check out.